Vibration signals are used in house hunting honeybee swarms to coordinate swarm takeoff. The model organism used in the research projects to examine vibration signals in honeybee swarms was Apis mellifera. The reason for this is that it's one of the most common honeybees found in the United States. Currently, it is known that there are several different factors that influence and control the house hunting process of honeybee swarms. The waggle dance is used in swarms to communicate location of nest sites. Piping is used to initiate bees to warm their thoracic muscles to prepare for swarm takeoff. Finally, buzz running is used in swarms as a final breakup of clusters for liftoff. However, while it is known that vibration signals are used by swarms during the house hunting process, not much is known about its specific role within the swarm. This leads to the research question: what is the role vibration signals play within a honeybee swarm during the house hunting process? In an experiment conducted by Donahoe, the research team wanted to examine how vibration signals correlate with liftoff of a swarm. In an experiment to test this correlation, there were 3 swarms: a test swarm, a manipulated control swarm, and an unmanipulated control swarm. In the test swarm, all vibrating bees were removed. In the manipulated control swarm, random workers and some waggle dancers were removed. In the unmanipulated control swarm, no bees were removed. The results of the experiment are summarized in this graph. The graph shows how long liftoff preparation took in each of the 3 swarms. The unmanipulated control, where no vibrating bees were removed, had the shortest liftoff preparation at around 40 minutes, while the test swarm, where all the vibrating bees were removed, had the longest liftoff preparation at around 160 minutes. The results are also summarized here. Beyond having the longest liftoff preparation time, the test swarm was also most likely to abort their takeoff or have trouble choosing a site. Other observations noted in the experiment is that there was no difference in a waggle dance activity or time it took to reach a consensus on nest site activity or site between the different swarms. Based on the results, it can be concluded that the vibrating signal plays a role in coordinating responses of other signals to stimulate swarm takeoff to a new location. In a separate study conducted by Vischer et al., his research team also wanted to examine the role that vibration signals played in takeoff of swarms. In this experiment, there were 2 natural swarms that were collected from trees and 2 artificial swarms. The natural swarms were named video swarm and citrus swarm. The video swarm was used as a control and was not included as part of the research results. The artificial swarms were named chala and eucalyptus. All the swarms were observed for 2 days. The results of the experiment are summarized below. The graph shows the number of vibrations observed within the swarm. The vibrations are recorded for days 1 and 2. It shows the vibrations at 9 a.m., 12 noon, and 3 p.m. indicated by the 1500 number as shown on the bottom axis. The dashed line on the bar chart indicates when the swarm took off. Based on the graph, vibration signals for all 3 swarms increased right before takeoff of the swarm. The chala swarm and the citrus swarm had a peak vibration of a half hour to an hour before takeoff. Meanwhile, the eucalyptus swarm had a peak vibration a half hour before takeoff. Based on these results, it could be concluded by the researchers that vibration signals are used to coordinate takeoff of a swarm to a new nest site, and that these vibration signals are used throughout the house hunting process, but increase right before takeoff. In an experiment conducted by Gilbert et al., the research team wanted to examine how vibration signals were impacted by nest site quality. In order to test this, the team used artificial swarms and presented each swarm with a high-quality and low-quality nest site at the same time. The high-quality nest site consisted of a 45-liter container that had 4 previously used combs, while the low-quality nest site consisted of a 22-liter container with 1 empty comb. The results of this experiment are summarized below. The solid bar indicates the high-quality nest site, while the line bar indicates the low-quality nest site. The graph indicates the percentage of nest site scouts vibrating or dancing. In regards to vibrations, there was no significant difference between the number of scouts vibrating at the high quality and low quality nest sites. However, there was a significant difference in the number of scouts dancing for the high quality nest site compared to low quality nest site. Specifically, more scouts danced for the high quality nest site. As shown by the graph, there was no difference in the amount of scouts vibrating for the low quality versus high quality nest site. As such, it can be concluded that the nest site quality does not influence the vibration signals of bees in a house hunting swarm. As a result of these studies examining vibration signals in honeybee swarms, it can be concluded that the overall role of vibration signals in the swarms is that these signals coordinate other communication signals that allow for takeoff. It was found that without vibration signals, a swarm could have longer takeoff time or completely abort liftoff. This was indicated through increased vibration signals right before takeoff and decreased liftoff preparation found in swarms that contain vibrating bees. Additionally, it was found that vibration signals do not play a role in indicating nest site quality, unlike the waggle dance. The significance of these findings is that beekeepers may have the potential of observing vibration signals to predict when swarms will take off. Furthermore, factors that prevent vibration signals could increase liftoff time of swarms or completely inhibit liftoff of swarms. This may negatively impact the honeybee's survival.